Good morning, students. In the last class, we have seen about the DC characteristics of the operational amplifier. In this class, we are going to discuss about the AC characteristics and circuit stability. So, before understanding the AC characteristics, we should know about the high frequency op-amp equivalent circuit. We have already seen about the op-amp equivalent circuit, so which containing the dependent sources AOL, VD and the output resistance R0 at the output side, and at the input side we have Ri in resistance. Like that, we have already seen the equivalent circuit for the operational amplifier, but the equivalent circuit is somewhat differ in the AC characteristics. So why it is come, we will discuss in this class. Okay, so let us see the high frequency op-amp equivalent circuit. So this is the equivalent circuit of an operational amplifier in high frequencies. If you see, there is no change in the equivalent circuit up to here. So V1 and V2 are the input voltages and the VD is the differential input voltage and Ri is the input resistance which is in the equivalent circuit of our operational amplifier, and up to here it is the input side. If you go to the output side, AOLVD will be the dependent voltage source that depending upon the differential voltage of or input voltage of the operational amplifier, which is also called as Thevenin's equivalent voltage source. And along with this voltage source, we have a resistance called R0, which is called as Thevenin's equivalent resistance R0. Okay, up to here the equivalent circuit is same what we are using for the small frequencies, but there is a capacitance effect, so which is added parallelly to our output circuit, which is called C. This capacitance will get added in parallel with the output of our operational amplifier equivalent circuit. So why this capacitor will occur? Actually, the operational amplifiers are building in a monolithic IC. In the monolithic IC, we are fabricating all the components on a single chip. In the chip, they will use some material to isolate between the one component to another component. If two conductors are placed next to each other and the material used for the insulating between the conductors will act as dielectric material, and these two conductors will be acts like a plates for the capacitance. Okay, so these all will forms one capacitor. Okay, I will explain you. So if entire IC is fabricating in a single chip, so there are a number of wires between the different chips. Suppose this is one chip and this is chip number 2, like this. There are some wires so which are used to connect the output of stage 1 to the stage 2, like that. These two are called the wires or conductors. In between the conductors, we have the material called substrate is there. This substrate is a insulating material, and this material will act as a dielectric for the capacitance formation, and these two connectors will act like a plates for the capacitor. Okay, so if an insulating material or dielectric material is placed between the two parallel plates, then there is a chance of forming one capacitance. So like that, if how many connections are there in the operational amplifier, that many capacitances will get added. Okay, so these capacitances are combinedly called as a single capacitor called C. Okay, so the equivalent capacitance C has been shown in the equivalent circuit of our operational amplifier. So in high frequencies, a capacitor C will get added to our output of our op-amp. Okay, let us see the gain. What will happen to our gain? The gain A is equal to AOL divided by square root of 1 plus F by FL whole square or F by F1 whole square. So here the gain is depending upon the frequency. Up to now, the gain is independent of the frequency. At high frequencies, the gain is depending on the frequency. So in this equation, you can observe square root of 1 plus F by FL whole square. So here F is the frequency applied to our operating frequency of our operational amplifier. Okay, so this R and C is forming the low pass filter now. Okay, then the gain is depending upon the frequency. Let us see the AC characteristics of our operational amplifier. For small signal AC application to OPAMP, we should know about the AC characteristics of OPAMP such as the frequency response, slew rate. These two are called as the AC characteristics. So when we are applying some AC signal to our operational amplifier, so we must and should know about the AC characteristics. Up to now we are applying the DC voltage, so the DC characteristics has been discussed. But now we are going to apply the AC signals. If you are applying the AC signals, then definitely we should know about these characteristics. So those characteristics are frequency response and slew rate. So let us discuss about these things. The frequency response, first of all. The frequency response is a graph drawn between the frequency and gain. Okay, the frequency response is a graph drawn between the frequency versus gain. On x-axis we will take the frequency and on the y-axis we will take the gain. Okay, so in order to draw the frequency response, the variation in operating frequency will cause variations in the gain magnitude and its phase angle. So we have already seen the gain equation of the AC high frequency equivalent circuit of op-amp. It is depending on the frequency. It is depending on the operating frequency. So the variation in the operating frequency, if operating frequency of the operational amplifier has been changed, then it will cause the variations in the gain magnitude. So therefore the gain also will changes and the phase angle also will get changed. Okay, at higher frequencies the gain decreases. So because of the capacitance effect added at the output of our operational amplifier, the gain will decreases at the high frequencies. Next one, due to the capacitance effect at the output of an op-amp, so the gain will decreases. This is called the frequency response. Let us see the derivation for the frequency response of a operational amplifier. In order to do the derivation, we are going to take the same AC equivalent circuit of our operational amplifier. So let us see output voltage V0. So the output voltage V0 is the voltage across the capacitor C. In this loop, if you observe, there is only one voltage source that is present, which is AOL into VD. Okay, therefore by using the voltage division rule, applied voltage AOLVD into across the resistance divided by the total resistance is the formula. So here applied voltage is AOLVD and across the resistance is the reactance of the capacitor divided by the reactance of capacitor plus the resistance R0. So see, V0 is equal to AOLVD into this one is minus JXC divided by R0 minus JXC. So this is the equation for the output voltage in this loop. Let us see the gain of this operational amplifier, which is V0 by VD. And the gain is the ratio of output voltage to the input voltage. Output voltage is V0 and input voltage is VD. So which is equal to AOL by 1 plus J2 pi F R0 into C. If you rearrange this equation V0 divided by VD and apply XC is equal to XC is the reactance of the capacitor, which is 1 by omega C. Okay, so A is equal to V0 by VD. After simplifying the above equation, we will get AOL by 1 plus J2 pi F R0 into C. Let us see. Therefore, we are taking it as A is equal to AOL, where A is the closed loop gain actually. So A is equal to AOL divided by 1 plus J into F by F1. F by F1. So where what is this F1? F1 is taken as 1 by 2 pi R naught into C in this equation. So 1 by 2 pi R naught into C has been taken as F1. So that's why we are getting it as F by F1 in the denominator section. Only J is the imaginary factor that is present here. So in order to eliminate the imaginary factor J, so we are taking the modulus for the amplitude. So modulus of A is equal to AOL by square root of 1 plus F by F1 whole square. F by F1 whole square. So this is the equation for the magnitude of the AC equivalent circuit, and the phase of the above circuit has been given as phi is equal to minus tan inverse of F by F1. Phi is equal to minus tan inverse of F by F1, where F is the operating frequency. For the frequencies F is very much less than F1, the magnitude of the gain is 20 log AOL in dB only. If the F is very much less than F1, if the F is very much less than F1, so small value by the large value, which results a small value. Therefore, the entire denominator will be equal to the 1 only. Therefore, the gain is equal to the AOL only. Okay, na? So that we are taking the 20 log in order to express the gain in terms of the decibels, which is 20 log AOL in dB. In this case, at frequency f is equal to f1, the gain is minus 3 dB down from the maximum value of the AOL in decibels. The frequency f1 is called as the corner frequency. So at f is equal to f1, what happens? The gain will be decreased by 3 dB times. In this equation, at f is equal to f1. So f1 by f1 will become 1 here. So 1 square is 1, 1 plus 1 is 2. AOL by root 2 will occur, okay, which will be the gain. When we apply the decibels, which is 20 log into AOL by root 2, then which is equal to the minus 3 dB less than the maximum value, where f1 is also called as the corner frequency. For the frequencies f is very much greater than f1, the gain will roll off at a rate of 20 decibels per decade. This is the frequency response curve of the operational amplifier. So at in the low frequencies, the gain is maximum, which is modulus of A in decibels. Okay, so here, after the corner frequency f1, the gain is getting roll off here. The roll off rate is defined as 20 dB per decade. Okay, up to 1 decade, it is decaying by 20 dB. At f is equal to f1, the gain was decreased by minus 3 dB. So this is the maximum value of the gain, and at f is equal to f1, we are getting minus 3 dB value from the maximum, and the gain is getting roll off at the rate of minus 20 dB per decade. If you see the phase plot for the same operational amplifier, so at f is equal to f1, we are getting the phase of 45 degrees. Okay, so this is about the frequency response curves of the operational amplifier. So let us see if the op-amp operates with more than one corner frequencies. Up to now, so we have only one corner frequency, which is f1. Suppose in the case our op-amp has more than one corner frequency, then what is the output gain equation? Therefore, gain A is equal to AOL divided by 1 plus J into F by F1. This is for one corner frequency, and for the second corner frequency 1 plus J into F by F2, and the third corner frequency so into 1 plus J into F by F3, where F1, F2, F3 are the three different corner frequencies of our operational amplifier. So where 0 is less than F1, less than F2, less than F3. So which means that the corner frequencies are greater than each other. So f1 is less than f2 and f2 is less than f3. So f3 is the biggest corner frequency, and this can be represented in S domain. A is equal to AOL into omega 1, omega 2, omega 3 divided by S plus omega 1 into S plus omega 2 into S plus omega 3, where omega is the angular frequency of the operating frequency. Okay, let us see the open loop gain versus frequency curve. So this curve is very important in examinations. There are so many times they are asking to draw the open loop versus frequency gain curve. So if you observe this graph, for this graph has been drawn for the multiple corner frequency operating amplifier. So in this type of operating amplifier, so there are so many corner frequencies. After each corner frequency, the gain roll off will be different. Okay, I will explain you what it is. So the gain roll off in the sense decrementing rate of the gain decrementing rate of the graph. So in this graph, the gain is getting decreased here. So continuously the gain is getting decreased here with the rate of minus 20 dB per decade. Okay, so let us see, on the x-axis we are taking the frequency, on y-axis we are taking the open loop gain in decibels. At low frequencies, the gain is maximum. It is starting from the maximum. Okay, so after the corner frequency f1, the gain is started decrement, and this decrement rate is minus 20 dB per decade. After the second corner frequency f2, the gain is again decreasing fast, which is minus 40 dB per decade. So in similar graph we can observe the separations, those are called as the decades. Okay, in the decades the gain decrement has been increased to minus 20 dB per decade to minus 40 dB per decade, and after the third corner frequency f3, the gain is decrement by at a rate of minus 60 dB per decade. So for every decade, the gain roll off was increased by 20 dB. Okay, at the first corner frequency or after the first corner frequency, it is minus 20 dB. After the second corner frequency f2, it is minus 40 dB. After the third corner frequency, it is minus 60 dB. Okay, this is about the open loop versus frequency of our operational amplifier, which is having multiple corner frequencies. Okay, let us see the slew rate. Slew rate is the next AC characteristics of our operational amplifier. Let us see another important frequency related parameter of an op-amp is the slew rate. The slew rate is the maximum rate of change of output voltage with respect to the time. It was specified in volts per microsecond usually. So this is the important parameter of operating amplifier. The slew rate will give us the maximum rate of change of output voltage, how fast our output is getting changed. Okay, this slew rate will discuss about it, and which will be expressed in terms of volts per microsecond. The volts per microsecond in the sense how many volts is getting changed for 1 microsecond. Like that we will calculate the slew rate, the effect of slew rate by using one square wave. I am going to explain you the slew rate effect. This is the input signal, which is a square wave. Okay, so this square wave has been applied to our operational amplifier, and if our operational amplifier has some slew rate, definitely the output is different from the input signal. So how it will be, see, up for the input signal from the plus Vm to minus Vm, the input got changed without any delay here. From the plus Vm to minus Vm, the input has been changed without any delay. If you observe in the output curve, to change the output voltage from the plus Vm to the minus Vm, it was taken some time. Okay, it is linearly slowly changing the output from the plus Vm to minus Vm. the time taken to change the output from the plus Vm to minus Vm after input has been changed. The time taken to change the output level after the input change is called as slew rate, okay, delta T, and the delta V0 is a change in the output voltage. The change in the output voltage, and delta T is the change in the time after how many microseconds or milliseconds the output has been changed to the present level. Similarly, here also you can observe the input has been increased from minus Vm to the plus Vm, but it is taking somewhat time to reach the minus Vm to plus Vm at the output side, so that the output was distorted. We can say the output has been distorted here. Okay, so this is the effect of slew rate. If the slew rate is more, then there is no problem. If the slew rate is less, then only we will have this type of distortion at the outputs. If the slew rate is more, which means that more volts can be changed in the microseconds, then definitely without any delay the output will be shifted from this volts to this volts. The plus Vm to minus Vm without any delay, it can get changed. So this is the effect of the slew rate. The reason for slew rate. There are usually a capacitor within or outside of operational amplifier to prevent the oscillation. We have already seen there is a capacitance which is at the output of our operational amplifier. This capacitor which prevents the output voltage from the fast changing input. Because of that capacitance which is added in parallel with the output of our op-amp, because of that this output cannot be changed fast. It will stop the fast changing of the output. It takes some time to charge and discharge. So because of that time, we are getting the delay at the output side. The rate at which the voltage across the capacitor changes is given by the formula dV by dt, which is equal to I by C, where I is the current, the charging current of the capacitor, and C is the capacitance. dV by dt is nothing but the rate of change of voltage across the capacitor, and this can also be written as, if you take the I as a common here, so I is equal to C into dV by dt. If you want to get the charging current, I is equal to C into dV by dt. So dV by dt can be written as I by C similarly, where I is the maximum amount of current furnished by op amp to the capacitor C, and the slew rate of the 741 op amp is slew rate is equal to dV by dt maximum, which is equal to I maximum by C. In the examinations, they may ask you the slew rate by just giving the maximum current and capacitance. We will see some problems also in this session. Okay, for a sine wave input, the effect of slew rate can be calculated as considered by using a voltage follower. So this is a voltage follower. We already know what is voltage follower. The voltage follower is a unity gain operational amplifier used to isolate the circuit. So the gain of this voltage follower is only one unity. Okay, so here you can see this is a non-inverting type of voltage follower in which we are applying the input signal Vs, which is a sinusoidal signal we are going to apply. So Vs is equal to Vm sine omega t. It is the representation of the sinusoidal signal, where Vm is the maximum or peak voltage of the sinusoidal signal, and sine omega t is the representation of the sine. Then the output voltage V0 is equal to Vm sine omega t only. Input signal is equal to output signal because the gain of the voltage follower is same. The rate of change of output can be given as dV0 by dt. Because of the high frequency, there is the effect of capacitance. Okay, so because of the slew rate effect, this output will get changed like dV0 by dt, the rate of change of output with respect to the time, which is equal to Vm W cos omega t. If you take the differentiation to the right hand side equation, so Vm is a is a constant which was taken outside. Sin omega t differentiation is omega into cos omega t. Therefore, the maximum, so if you apply the sinusoidal signal, we are getting the cos signal here. Input signal is a sinusoidal signal and output signal is a cos signal. The maximum rate of change of output when we got the maximum rate of change of output when the cos omega t is equal to 1. Therefore, the slew rate is equal to dv naught by dt at maximum, which is equal to omega into Vm. The cos omega t will becomes as a 1. Therefore, the slew rate can be given as the here omega can be represented as 2 pi f into Vm volts per second. Thus, the maximum frequency f maximum at which we can obtain an undistorted output voltage of peak value Vm is given by f maximum is equal to the slew rate divided by 2 pi Vm. If you rearrange the equation in order to get f is equal to slew rate divided by 2 pi Vm. This is the equation where f maximum is the full power bandwidth, where f maximum is the full power bandwidth. So in the problems they may ask you to calculate the full power bandwidth of the operational amplifier by just giving the maximum peak value or the peak to peak value and the slew rate value. Okay, or else they may ask you to calculate the slew rate of the op amp by just giving the f maximum and Vm values. Okay, so we have to use this formula in the problems.